Hey y'all, today we're going to be taking acid-base discussion one step further and talk about what happens once an acid reacts, once it gives up that hydrogen. What happens to a base once it reacts, once it accepts that hydrogen. These are going to be called conjugate pairs, and today's video is focused on not just identifying them, but also trying to identify whether they themselves are acids or bases. Let's go ahead and get started. In the last video, we identified what makes an acid and what makes a base. And we talked about how you need to memorize the 7 strong acids and the 8 strong bases. That's really important, especially in this video, because we're going to apply that. Any acid that's not a strong acid is a weak acid, and any base that's not a strong base is a weak base. We talked about how strong acids fully dissociate, strong bases fully dissociate, but weak acids and weak bases find equilibrium. And today we're focused on that idea of what happens when a weak acid or a weak base finds equilibrium. We're going to go ahead and get started with some quick definitions. When an acid gives up its hydrogen, the anion of that acid is the conjugate of that acid. We would know this as the conjugate pair. So the acid and its anion represent a conjugate pair. For strong acids, that conjugate has no effect on the pH of the solution. It's so weak we would consider it negligible. Sometimes I even call it pathetic. When it comes to the cation of a strong base, much in the same way, once it dissociates in water, it has no effect on the pH of the solution. And as a result, it is a negligible or pathetic conjugate acid. So when we look at strong acids and strong bases, their conjugates aren't even considered to be acids or bases. However, weak acids and weak bases, the game's a little different. So let's talk about that. When a weak acid goes into water, it'll dissociate into 2 things, an H plus and its conjugate base. Now, here's the thing. The conjugate base of a weak acid is a weak base. Simultaneously, if a weak base goes into water and dissociates, all of a sudden what's going to happen is it's going to create its conjugate acid. So a weak base will also have a weak conjugate acid. Let me repeat this. A weak acid's conjugate is a weak base. A weak base's conjugate is a weak acid. This is very different than with the strong acids and strong bases. Remember, the conjugates of strong acids and strong bases are negligible acids and bases themselves. So when we look at a weak acid or a weak base, though, this is what gives us an equilibrium. Strong acids and strong bases don't find equilibrium because those reactions will never go in the opposite direction. They'll only go in the forward direction, dissociation. But with weak acids and weak bases, they can equally go in both directions, but maybe not so equal. Because here's the thing. A stronger weak acid produces a weaker weak base as its conjugate. A stronger weak base produces a weaker weak acid as its conjugate. The reason we can do this and look at this is when we think about equilibrium. So go back to earlier equilibrium. The more a reaction favors one direction, the less it'll favor the other. So if an acid is stronger, it'll favor that forward direction of the acid dissociating more. And as a result, the base going in the reverse direction won't be quite as favored. It won't be quite as strong. So the stronger the forward direction, the stronger the acid, the weaker its conjugate base is going to be. But be aware. Please be careful. A weak acid's conjugate is a weak base. A weak base's conjugate is a weak acid. But much like a pendulum, as one gets stronger, the conjugate gets weaker, and as one gets weaker, the conjugate gets stronger. So take a look at this chart real quick. Let's compare acids and conjugate bases. So at the top, you can see that as we get further and further to the left, the strength of the acid increases. If you look down at the conjugates, which are, remember, these are the acids without the H+. So if we strip the H+ from HClO2, we end up with ClO2-. ClO2- is the conjugate base of HClO2. ClO2- becomes HClO2, and therefore HClO2 is the conjugate acid of ClO2 minus. So HClO2 is one of the stronger weak acids, which means that ClO2 minus is one of the weaker weak bases. On the other end of the spectrum, HPO42 minus is one of the weaker weak acids. So its conjugate, PO43 minus, which is, again, we've lost that H plus, is one of the stronger weak bases. In a future video, we're going to put numbers to this, but right now you need to just understand the concept that a stronger weak acid creates a weaker conjugate base, and a stronger weak base creates a weaker conjugate acid. One thing to be aware of is this can be applied using salts. We can actually predict whether a salt will be acidic in nature or basic in nature. In other words, when we put that salt into water, is the pH going to go down or is the pH going to go up? The way we determine this is by looking at the cation and anions of those salts. If we have a weak acid or weak base within that salt, we will know how the pH is going to be affected. In order to do that, we need to make some predictions. So let's take a look at one. Here I've got ammonium chloride, NH4Cl, really common salt that we deal with a lot. What I'm going to first do is look at the cation ammonium. Now, NH4 plus ammonium by itself might not appear to be an acid or a base. However, when we think about ammonium, if I remove an H plus from that ammonium, I get NH3. NH3 is one of my common weak bases. Well, if it became ammonium because I removed an H plus, then ammonium must be the conjugate acid to the conjugate base, which is ammonia. So ammonia is a weak base. That means ammonium is a weak acid. Okay, that tells us something. Look at the Cl minus. That's the other part of this salt. Cl minus, the conjugate, if we added an H plus to it, well, that's HCl, a strong acid. And HCl is a strong acid, which means its conjugate, Cl minus, is pathetic. It's negligible. It has no effect on the pH at all. So here we have NH4 plus, which is the conjugate acid of a weak base. Thereby, it's a weak acid. And we have Cl minus, which is the conjugate of a strong acid. So it's pathetic. Doesn't affect the pH. Therefore, the acidic pH would be as a result of the NH4 plus. And this would be considered an acidic salt because the NH4 plus would lower the pH below 7. The Cl minus, it does nothing. It's mostly a spectator in this whole process. Here are two more salts. I want you to take a look at these and predict whether in water these would increase the pH as alkaline salts or decrease the pH as acidic salts. Or perhaps maybe they don't affect the pH at all. Take a look, make a prediction. When we get back, we'll talk about it. The first salt here is potassium cyanide, KCN. Now, potassium, looking at just the cation here, is the conjugate of potassium hydroxide, one of our 8 strong bases. That means potassium is negligible, has no effect on the pH whatsoever. Cn minus, however, our anion, is the conjugate of hydrogen cyanide or hydrocyanic acid. HCN is a weak acid. It's not one of our 7 strongs, so we know it's weak. As a result, Cn minus is itself a weak base. So K plus has no effect on the pH. However, Cn minus would cause the pH to increase above 7. Therefore, this would be considered an alkaline base because when the Cn minus interacts with the water, it would strip a hydrogen from the water, creating HCN and OH minus. And that OH minus is what's going to increase the pH above 7. Now, the NaCl is a bit of a trick here. The reason is because the Na plus is the conjugate of sodium hydroxide, one of our 8 strong bases. So it has no effect on the pH. Doesn't change it from 7 at all. The Cl minus is the conjugate of HCl, one of our 7 strong acids. So it has no effect on the pH. Does nothing to it whatsoever. This means that both our cation and our anion are negligible. And as a result, our pH of an NaCl solution would still be at 7. It's a neutral salt. So that wraps up today's video. Let's do a quick recap. Today, we looked at how to predict conjugate pairs of acids and bases. We then applied that to salts and predicting whether a salt would be acidic in nature or basic in nature. Remember, one of the most important things is that the conjugate of a weak acid is a weak base, and the conjugate of a weak base is a weak acid. The conjugates of strong acids and strong bases are negligible. They don't affect the pH at all. And so when we look at salts, all we're going to do is look at the cation, look at the anion, and make an independent prediction of each one as to how it'll affect the pH. That's how we're going to know whether the salt will cause the pH to go up or down. Today's video was written, directed, edited, and produced by Maddie McDaniels. Thank you all for watching. I hope you enjoyed it, and I'll see you in the next one. Woohoo. Yes, I love chemistry.